All right, just I want to cover the conceptual stuff today, and then we'll finish this up next week. I'm working on Wednesday.
See what's going on, and that's when I pulled out my camera and I noticed there was a gentleman on.
All right, so
Anything was just in shock.
This guy, as soon as he goes across the transformer, he gets shocked, which means that there's going to be an enormous potential difference, voltage difference across the transformer. All right, so what's the transformer and what's the purpose of it? I think somebody said that the purpose of the transformer is to increase or reduce the voltage, right? All right, so how does a transformer work? How do you increase the voltage at well, and how do you reduce the voltage at well? So those are the discussions that we will have. We talked about Philo Farnsworth not getting the recognition that he deserved. By all means, he should have gotten some money, and if he didn't, he should have gotten some recognition for what he did. If he did, he's not the only person. By all means, Nikola Tesla should have won the Nobel Prize 3 times. Not only did he not win the Nobel Prize, but also the fact that he was almost forgotten by the time he actually passed away. All right, so how did that come about? It's got something to do with what happened between Tesla and Edison, obviously. So the question is, what is the history behind it? We're watching a video on Faraday.
For energy.
A lot of we've been discussing in physics 2 can be traced back to one person and one person only, and that's Michael Faraday. Physics 1 is all about Newton, the physics 2 is all about Michael Faraday. The difference between Newton and Faraday is Newton was also a genius mathematician. Faraday, on the other hand, could not even handle basic algebra.
Inspired by his religion. For him, the problem was a way to understand God's hidden mysteries.
There was a small, almost persecuted group in London called the Sandemanians. They were religious, not really a sect, they were just a small subset, sort of like Quakers. Faraday was a member of that group. It was a very gentle, decent group. They believed that underneath the whole surface of reality, everything was created by God in a unified way, that if you opened up one little part of it, you could see how everything was connected.
Michael Faraday was someone who, like Einstein, thought in terms of pictures.
Faraday was different from anybody else. He had a flair for understanding his experiments, for understanding what was really going on inside them.
By methodically placing a compass all around an electrified wire, Faraday started to notice a pattern.
What everyone else at the time had been taught was that forces travel in straight lines. Faraday was different. Faraday imagined that invisible lines of force flowed around an electric wire. And then he imagined that a magnet had similar lines emerging from it, and that those lines would get caught up in this flow. It was a bit like a flag in the wind.
But Faraday's great leap of imagination was to turn this experiment on its head. Instead of an electrified wire moving a compass needle, he wondered if he could get a static magnet to move a wire.
I've never seen you like this, Faraday. You look like a happy child. I'm shaking, Newman. Underneath, I'm shaking. You see, John? You see? Yes.
This is the experiment of the century. It's the invention of the electric motor. Pull up the wire really big, and weight them, and drag on. But more importantly, he's inventing a new kind of physics here.
Although he didn't realize it at the time, Faraday had also just demonstrated an overarching principle. The chemicals in the battery had been transformed into electricity in the wire, which had combined with the magnet to produce motion. Behind all these various forces, there was a common energy.
All right, so Ørsted is the guy who discovers that the current generates magnetism. So the question was, given the fact that current generates magnetism, is it possible that we can also generate current using magnets? So people were looking for symmetry in physics. So magnetism is generated by current. Can you generate current by using magnets or magnetism? This is so happens the answer is yes, as Faraday discovered about 10 years later. This is 1830s.
A couple of months earlier, Davy had been elected president of the Royal Society, which was the elite body of English science. But then he saw this great discovery published in the Quarterly Journal of Science. I don't know if he was envious, but he certainly saw that this young man who'd been his assistant, this mere blacksmith's son, had come up with one of the greatest discoveries of the Victorian era.
Davy accuses Faraday of plagiarizing similar work from another eminent British scientist, William Wollaston.
So, Faraday, what does Wollaston make of all this?
He's written to me and assures me that he's taken no offence. And he acknowledges that what I published was entirely my own work.
Right. Davy is just being an ass.
But will Davy now retract his allegation?
Sadly, no. In fact, he's still vehemently opposed to you being elected a member of the society.
Really? And what do you think?
Faraday, my dear boy, you have my vote.
Hang on. I don't believe you even have Wollaston's.
What a mess.
Well, no matter. No matter. It's the science that counts. So tell me, how does this wire of yours spin round its magnet? What mysterious forces are at play?
There seems to be an electromagnetic interaction. In my mind, I see a swirling array of lines of force spinning out of the electrified wire, like a spiraling web.
But invisible lines of force, it's all a bit vague, isn't it?
Faraday, might I have a word in private?
Certainly.
Listen, Faraday, let's stop this nonsense. I want you to take down your ballot paper from the notice board.
Sir Humphrey, I see no reason to take it down. My friends have proposed me. It is they who put the paper up. I will not take it down. Good day.
Faraday was elected to the Royal Society. Davy died 5 years later, a victim of his many gaseous inhalations. In time, Faraday's world of invisible forces would lead to a whole new understanding of energy. He'd started what Einstein would call the Great Revolution.
Okay, guys, so what's Faraday's background in? This guy is...
Blacksmith?
Okay, his dad was a blacksmith. Give yourself 5 points for that one. He was a bookbinder.
Bookbinder.
So that's perfectly fine. I think you're in the ballpark. He doesn't have any formal education in sciences. He didn't go to college. He's not a college graduate. He's got practically no experience in mathematics. I don't know if he could even handle basic algebra. And just about anything and everything that we discussed so far actually came out of this guy's brain. Imagine that. The reason why physics is so visual up to this point, we're talking about the electric field lines, the magnetic field lines, and all that stuff, because this guy did problem solving conceptually as well as visually. He's considered to be one of the greatest physicists. And not only one of the greatest physicists, but he's also the last physicist who could not handle mathematics. Obviously, you can't do physics without math today. Amazing mind. All right, so here's what he discovered. As this one happens, yes, you can generate current. But what you need to have is a loop of wire, and then you need to have a magnet. And notice what happens when you thrust the magnet in the forward direction. The intensity of the magnetic field is going to increase, or you will intensify the magnetic field intercepted by this area. So the current is going to go one way. And then when you move the magnet away, you will reduce the intensity of the magnetic field intercepted by this area, so the current is going to go the other way. That's it. All right, so that's what he discovered. All right, so you got a magnet, you got a loop. If the intensity of the magnetic field within the loop is not changing, nothing happens. As soon as you vary the intensity of the magnetic field inside the loop, the current is going to go one way when you increase the intensity. And when you reduce the intensity, the current is going to flow the other way. All right, so this is known as alternating current because the direction of the current keeps alternating. So simply stated, if you vary the strength of the magnetic field inside the loop, that's what generates current. So the current is generated by varying the intensity of the magnetic field inside the loop of wire loop. All right, there are a couple of ways you can change the intensity. One way of doing it is just get a magnet in a loop and then move the magnet just like that. It's going to look obscene, but that's the way it is. So move the magnet back and forth towards the loop. But the other way you could do it is just get a loop of wire just like this and place it inside a constant magnetic field region, inside a constant magnetic field, region of constant magnetic field. And then just vary the area exposed to the magnetic field, which means that you can actually move the area back and forth, or you can just spin it inside a loop. Kind of the
But
way
the effect
this guy will
can
do.
be seen in a simple loop of wire connected only to a meter which measures electric currents.
If I move this conductor in the presence of the Earth's magnetic field, then that gives rise to currents. Once you have currents, those give rise to magnetic fields.
Deep in the heart of the Royal Institution, Faraday conducted experiments to understand how they were linked. In one experiment, a copper wire carrying electricity somehow provoked a nearby compass to move. In another, Faraday tried to do the opposite. Use a magnet to generate electricity.
Which led him to invent the electric generator, which is an example where you have a permanent magnet and a coil of wire.
So the wire is wrapped around this bit.
Wire's wrapped around the cylinder, and you push and pull the magnet in and out of the cylinder to generate an electric current.
I like the lights. What's the Christmas lights for?
Well, that's to show the electricity is passing.
Oh, okay.
Faraday did not use light-emitting diodes.
I think he should have done. That was his great mistake.
And all electricity power stations throughout the world use this principle of generating electricity that Faraday discovered down here in 1831.
Faraday had generated electricity simply by moving a magnet through a coiled wire. A discovery that would forever be associated with his name. But he was left with perplexing questions. There was no physical contact between the electric wire and the magnetic needle that moved, nor between the moving magnet and the copper coil. They were affecting each other through seemingly thin air. How could that be?
Now, what Faraday thought was happening was that there were lines of force coming out at the end of the magnet, which were then cutting the wire within the coil to move electricity around the coil.
The idea of mysterious lines coming out of the magnet to generate electricity may have seemed outlandish, but Faraday had a simple experiment that could prove their existence.
So he took a very powerful permanent magnet, placed some paper on it, sprinkled iron filings over it, just to represent the lines of force.
It never fails to impress that.
Of the magnet, and you can see it's still three-dimensional.
So these are coming up here and swinging around, and then coming down into this bit here.
And Faraday sort of made permanent examples of this and sent them around to all his mates in Europe to show the space had structure as a very strong argument for his field theory.
So Faraday thought there was an invisible force field at work here.
Literally a field. I mean, Faraday still brings the word field into science, and it's invisible, as you say. But, so this is why this is just a representation. It shows the existence of those invisible lines.
Faraday's iron filings experiment revealed the existence of an invisible field stretching out into thin air. These fields, he thought, were responsible for the experimental results he'd seen. Despite having physical proof, Faraday lacked a mathematical description of how the field was generated, or why it affected things around it. Without a mathematical proof, many 19th century scientists dismissed the theory as speculative.
All right, so okay, guys, just find chapter number 22, electron nodes. All right, so AC versus DC. AC is going to be our alternating current. It's so named because the direction of the current is alternating. All right, so this is an interesting day. So, okay, so the alternating current requires that we're using magnets. All right, so this is the sign that we get to use for it. All right, notice that this is just going up and down, just like that, which means that the current changes direction. This is also a sign notation going up and down. What that means is if this is the current, it's just going up and down within a time axis. That's what it means. All right, so the voltage is the one which is going up and down, which means that the current is going to do the same. Alternating current is generated by magnets. How they're generated by magnets is something which is explained by the Faraday's law. Okay, so direct current, direction of the current is constant. That's what it means. Which is generated by a battery. So those are the main differences. All right, so the Faraday's law, 1830 or 1831, we're on this. Okay, so there are two ways you can do it. Just change the intensity of the magnetic field, intercepted by this region, the area of a loop. All right, so if you increase the intensity, the current goes one way. If you reduce the intensity, the current is going to go the other direction. Okay, so this is a mathematical statement regarding what I just described. All right, so the intensity of the magnetic field is the one which is changing here, delta V, delta T, which is how fast you change the intensity of the magnetic field, intercepted by within this region. So you got this area. So that's what induces current. All right, let me just change this a little bit. This is just a little bit too colorful. All right, so just get rid of that. All right, so the statement here is if you vary the intensity of the magnetic field within this area, it's going to induce current. All right, so I'm varying the intensity of the magnetic field through this region, and it induces current. Vary the intensity of the magnetic field through this area, it induces current. So that's one way of doing it. There's a second way of doing it. All right, once again, let me just get rid of this one. The second way of doing it is, here's your current loop. What you do is you kind of spin this loop in this direction. By spinning it, you're varying the area exposed to the magnetic field. So you end up varying the cross-sectional area which is exposed to the magnetic field. All right, so this is how fast you're varying the area which is exposed to the magnetic field inside a constant magnetic field region. So that also induces current. So varying the area exposed to the magnetic field. Area of the this is the area of the loop exposed to the magnetic field is also going to induce current. All right, so you can vary the strength of the magnetic field inside a loop. That's going to induce current. Or you can keep the magnetic field constant and then vary the area which is exposed to the magnetic field by spinning.